Hey guys, I'm inside recently set up additive manufacturing facility of Indian Institute of Science. You can see this alien looking robust brutal machine. It's a 3D metal 3D printer, and I'm sitting with one of the pioneer in additive manufacturing or 3D metal printing in the Indian scene. I'm sitting with Swapnil Bhure. Thank you so much for making your time, and I've been waiting since a long time to have a discussion with you.
Yeah, thank you for having me here.
Yes.
So we were in the discussion to have this podcast, but I think after 1.5 years or so, we were able to make it possible.
Typical scientist life. So, okay, what is this machine? This is weirdly looking.
Yeah, so that is just a console panel. So it has a monitor there which is off, and inside that you have some electronics, the computer, and that is what controls this metal 3D printer.
3D printer, okay.
Yes.
So you make designs here.
Yes.
And implement it there.
Yes, so whatever codes that would make the printing possible, all of that is done through this.
What is the keyboard? How do you control
it's
that?
There inside.
Okay.
Yeah.
Why is this emergency knob here?
No, because we are working with laser. If something goes wrong while printing, you just press the emergency.
And we'll stop it.
Yeah.
Okay.
We have a CNC base and then we have a laser. So now there could be possibilities that CNC goes and hits to some other sample that you have printed or goes haywire. That's for emergency.
Nice.
So that's a...
So how this machine is superior?
Okay. So it has a much stronger, as you said, a very rugged build.
Right.
Yeah, okay. So this itself, I think, this frame, whole thing itself was about 2 tons, 1.5 tons.
One frame.
Yeah, this whole structure itself. So the laser head the laser source that we got, that's the state-of-the-art laser. In general, whatever a laser can do for this additive manufacturing process anywhere in the world, we have all of the features in
Nice.
it. Even the laser is so it comes as a wave. So when it falls on the substrate, so the energy density or the intensity is not uniform in that whole circle. Okay, so that can be varied. So we have a 3-core fiber laser. So where you have one central circular laser beam coming, then you have one ring, and then you have another ring. And then there are some advanced applications for which to control again the microstructure. You can engineer different strategies by this laser. So that's the laser part. The machine part, it's so rugged that even when we run it at its max speed, which is 200 mm per minute, no vibration at all.
200 mm per minute means 200 mm in the height, right? In the layer.
In the XY motion. And even when it accelerates, so when it goes to one end and then it has to again go back, so it slows down and then it comes back, right? So all of those small acceleration, decelerations would lead to some vibrations. So those are very minimal. In the previous machine that we had access to, you can hear the machine.
Right.
That's one part. Then the laser head. So laser head is where the optics sit. So we have collimator adjustment possible for this laser head. What that allows us to do is change the spot size of the laser. So let's say you do not want so much concentrated heat in a small region. You want a larger spot. So that can be done. Then we have infrared camera, which looks coaxially through the nozzle from where the laser comes. So that way we can see the melt pool, the shape, how it is moving, and how solidification. It's a grayscale infrared. Then we have inline pyrometer also. It's a dual wavelength pyrometer. So in general, the pyrometers require calibration by specifying the emissivity of a particular material. So when the laser hits and whatever radiation it emits, So that is captured by the
Pyrometer.
and then would give you the temperature reading. But what dual wavelength pyrometer does is it removes the material dependence. So now you can have different materials, you can work at different temperatures, but because it detects two wavelengths, so it has that emissivity which gets cancelled out of the equation, and then it is able to give us the right temperature. So that's the
How much would it cost?
So I think CNC would be some 60 lakhs something. The laser head would be, I think, about 80 lakhs something, and then the laser source would be around crore, and then and then the advantages here,
Sensors.
we can work with there are so many other peripherals, small things.
3CR easily.
Yeah, but because this was assembled together, we were able to get all the best that we could get in this much amount. If it is put into a commercial machine, obviously it would be way more expensive. So, and the great part was that this company who integrated all of this, because the laser head is coming from Germany, laser is coming from US, and the CNC bed, these people are manufacturing in India. And then all of this has to be controlled through the program. So they integrated all of that together,
hardware and
into
software.
hardware as well as the software part of it. So that was something great.
That's an Indian manufacturer.
Yes. Interface Design Associates.
Based in Bangalore.
No, they are based out of Navi Mumbai and Nashik.
Nice. So let me come to this one. So
there's another point.
Okay.
We can put this in vacuum, so we can do all sorts of the titanium and all the oxidizing materials. So they had to take into account even those things while building this. And plus, because we have a good collaboration with them, if there would be any feature or something that we would need, they are willing to add on into the software or the hardware part. So that gives us a full flexibility to use this machine.
Okay. Let's get into 3D printing in general. How do you describe 3D printing, and how and why did we get into metal 3D printing?
Everyone knows normal 2D printing, which is the printer. Okay. On a 2D page, it will print something. So now to build a 3-dimensional structure, that's just 3D printing, okay, as the name says.
Right.
But its origin came from the rapid prototyping. So in 70s, 80s, 90s, the models for any, let's say, automobile or any machine would be made out of either clay or, some certain materials. And then to increase the speed of the prototyping, then came this rapid prototyping where you make a CAD model and then you print with polymers. So that's how the polymer 3D printing started long time ago. And so it boomed, and then somewhere in 2000s, the development would be in 1990s, but somewhere in 2000s, the actual metal 3D printing took up. So then people thought, okay, you can make whatever CAD model you can make, you can print that model using a polymer 3D printer. So, and the clear advantage is that if there is a design that you can model, so whatever you can imagine, you can
make
model,
it.
and then whatever you can draw a model of, you can print it. Okay. In general, any of the metal manufacturing processes, be it casting, so there you need to make a mold, pour the liquid metal into it. Then that creating the mold itself is a very complicated and sophisticated process if you have a complicated geometry. And then there are certain geometries which would be very difficult to make through the casting process. So then what people would do is you cast it and then you machine out some region and then make the geometry the way you want it. But then what if you have the geometry, some complicated geometry, what if you can just print it directly with metal? So that was the idea. So what if we can take that polymer 3D printing type technology and can we do it for metals as well? So that would open up a lot of opportunities in terms of what we can design and manufacture. Plus, the manufacturing would become simpler. So making a cast block, that itself is it's a craft. Okay, and it's a complicated
what is
process.
the process of making a cast?
Okay.
Very interesting. Like, is it a human manual labor involved in making
I think now machines do it. So there are now different types of casting processes. Maybe you might have seen roadside. No, there will be people
Welding.
No. So you get your scrap metal, some old fan or something lying around in your house. You take those metals to them. They'll have a sand mold. And you give them, so sometimes they will have their own design. Let's say you want to make a sculpture or some pot or something. Okay. And so they will have a particular sand of the right composition and then the right moisture content, rightly compacted. And then they would just make the impression of the sculpture or whatever part you would want to make into that. Okay. So, once you make a cavity out of the
sandball,
out of the whatever piece geometry you have, and then you pour the liquid metal into it, and then you let it cool. Okay. So they would just heat the whatever scrap that you gave them. They heat up, melt it, and then pour it, and then it solidifies, and then you get the structure. So that's the most crudest form of the casting. Simplest. Okay. And then there are some sophisticated methods. So one is investment casting, where you make whatever geometry that you want to cast. So you would make a mold out of wax, and then you would cover it with the ceramic coating, and then you would put it in an oven. So you would melt all of the wax, okay, and then you are left with the cavity. Then you pour the liquid metal into it, and then later on, through chemical process, you would remove the outer ceramic coating also.
So you get the metal cast.
Yes. So that's one of the sophisticated process, and usually for complicated geometry, that's what people use.
A lot of human input was needed in terms
to
of
come to this.
Yeah.
Yes, to come to this. So I would date this to very old days, the
printing era.
No, even before that, the metal age, the copper, stamps they used to make, and then iron tools.
Wow.
So this casting technology goes way back.
You would say that was
casting
the
as well as some forging.
Stone Age of manufacturing.
Yeah.
Yeah. Okay.
So that's where it started, and then now because of technology, we have machines doing this stuff, but still human input is still required for this. So that was the
evolution of metal 3D printing.
Yeah. And then where were we at? The question
casting. It was about casting. So metal 3D printing would simplify casting.
Okay. Yeah. So now, since we have, now there is a limitation to how complicated a geometry can be using this particular, even with the investment casting process. So I'll give you one of the example which we are aspiring to make through my research. My research is kind of the background to get to that stage. It will take few more years to actually be able to bring this geometry. So every aircraft that flies, okay, almost every aircraft, okay, not the normal propeller ones. So almost 70-80% of the aircraft, so the engines, if they are using something called as gas turbine engine, which we see in most of the commercial aircrafts. Okay, I think I'll have to explain a little bit of that. To imagine the gas turbine engine, so you take a Indigo flight and maybe 320 or something, and then you see a a big fan, if you're taking, going into the plane,
Yeah,
from the front gate,
the turbine fan,
big
big
fan that you see. Okay, so that is so that fan sucks in the air, and then behind that fan, then you see that the shape is
Right.
kind of conical. No? It narrows down
Right.
slowly as
Right.
it goes towards the back. So it has some compressor blades. So this air gets sucked in, gets compressed. Okay, and then there is a chamber in which the fuel is injected. Now this compressed air combined with the fuel, it creates a blast, and then it ejects out the air from the back. Okay,
with a lot of force.
yeah, with a lot of force, and that generates the thrust to make the plane fly. Yeah, and yeah, sorry, I'm spacing out in between.
Yeah, that's fine. There's a lot of fragments here and there you have to connect. There's a lot of Java,
Yeah. No, and then plus because we are in the setup.
Right, okay.
Yeah. Wait, so where was I? Yeah.
Jet
So
engines.
now this hot gases. So this combustion, so the temperature in that combustion chamber would go to 300, 400 degrees Celsius. Okay, that's the temperature. Most of the metals would melt. Now the gases are exiting at that temperature. Now you need something. So you need something which can sustain those
That
high temperatures
for a long time.
For a long time. Second thing, you need some material so that you can extract energy out of it. I mean, that's the goal. You did that combustion so that you can extract energy, and then that would make it propel.
From heat energy, right?
Yes. So those hot gases which exit out of that combustion chamber. So next to that, you have something called as turbine blades. Okay, and so the gases at high pressure and very high temperature pass through those blades, and that makes them spin, and then that generates. So then there are few stages of those blades so that you extract as much energy as possible to generate the thrust. Now these blades have very complicated geometry. I mean, over several decades, people have come up with better and better materials as well as better geometry to extract more energy out of it. So the material which people have been using are nickel-based superalloys. Okay? So back in 50s, 60s, 70s, so people started using certain nickel-based superalloys. So now, whenever people speak of nickel, they always call nickel-based superalloys. They use the word superalloys. Usually you'll have alloys, iron alloy, aluminum alloy.
Alloy is a mixture of metals, right?
Yeah.
What is superalloy?
So what is superalloy? So they have superpower because of which they are called superalloys.
Okay.
The superpower that they have is that even at very high temperature, let's say close to even 0.8 or 0.7 times of their melting point, they undergo very less plastic deformation. A part subjected to loading at high temperature, so the deformation that happens, that's the creep. And this particular nickel alloy, so these are way more resistant
to high temperature and pressure.
So deformation at high temperature. So usually other metals will become soft, you can hammer them and then shape them. So that's one important superpower that they have. Now the second thing which the engineers realized over the decades of research is that somewhere I think in 70s, they understood that, okay, so the failure of the blades is mostly happening at the grain boundaries. Okay, I think to explain that we need to go to the microstructure.
We'll get into the science of it eventually.
So again, the nickel-based superalloys, they can withstand very high temperatures, but then as I said, the temperature that is seen by these blades is actually 1200, 1300, 1400 degrees Celsius, and that is close to its melting point.
And also exposed to a lot of time, right?
Yeah, exposed to a lot of time. So for that, what we have is something called as cooling channels. So a cold gust of air would be pushed into the geometry of the blade, and then through those holes. So I mean, one thing is these blades will be covered with something called as thermal barrier coatings. There are some ceramic based coating so that they can so the actual metal sees slightly lower temperature, and then on the top of that you will have this cold gas coming, and then the geometry is such that when the air exits from the leading edge of the blade, so it flows very close to the blade and it forms a thin layer of cold air which protects the blade. Okay, so now it's a very sophisticated and complex geometry. Okay, and again the process to make this blades is also complicated. It's through investment costing, but has several steps. So my research is on can we make it possible to make these blades using additive manufacturing? If we can do that, so still we are limited by the kind of geometries that we can make using the traditional casting route. Plus it's a time-taking process. Here it's like so one blade we might be able to print in half an hour, 1 hour tops. And there, through the traditional process, it would take hours or days to make blade. I mean, obviously they make it in bulk, but still.
So that is your point of your research.
Yeah, so that's the point of the research.
And
that's the motivation that, okay, can we make it? So this is as sophisticated as something can get. So we thought if we can make it possible to print a blade, then I think you should be able to do
anything possible with the metal.
With the metal using this process. So that was a very daring topic to choose.
Wow.
We have certain microstructural things. I think we'll get to that. Yeah.
But let's explore from the bird's eye point of view.
There's one more point I would want to add. It's a complicated geometry, and the design is also limited by the manufacturability or the machinability. So some metals, they are not so easy to machine because how hard they are, and they are prone to cracking if you try to machine it.
What do you mean by machining it?
Machining in the sense you'll use some lathe cutting, drilling to bring it to the actual geometry.
Right? Usable form.
Yeah. So some materials are not so friendly.
Like titanium.
Yes, titanium, and then certain nickel superalloys. So
very hard to machine it.
Yes. So the material that I have used in my PhD, that's also hard to machine. So even in such cases, you would want to make the geometry as close to what you really want, so that you have to do minimal machining.
That's where 3D metal printing helps.
Yeah.
One is creating complicated geometries possible.
Yeah.
And one more handling non-machinable materials.
Yes. So I mean, as of now, there is still certain amount of machining that is required, but I mean, eventually
major
we'll
part
get
to get there. Yeah. If we stand on the high ground and see what has been happening in the 3D printing. So 3D printing started with the plastic resins and things like that. In 2000s, we got into metal.
Maybe I think its origin would be in the previous century. But yeah, I mean...
what's the history of it? Do you understand the history of it? It's interesting to hear.
Yeah.
Who realized metal 3D printing, and was it an accident or was it...
I don't think that was an accident, because people were doing cladding processes, people were doing welding. Okay. So one of the additive manufacturing process is also wire arc based additive manufacturing, where it's very similar to welding, where usually people would have seen you have a rod which is sometimes consumable, you melt it and you deposit it.
That is metal 3D printing, right?
Yes. So now if you just connect it to automate it, Yeah, and if you do it layer by layer to form a geometry, that's 3D printing. That's the
Right.
simplest form of it.
Correct.
So it's kind of an extension of welding process, as well as a bit of cladding process as well. Okay, I'm not very much aware of that, so I think we'll not talk about
but
it.
that's a nice
Yeah.
analogy. I'd never thought about welding as a metal 3D printing.
Yeah.
So okay, then how it has been evolving, the machine 3D printing?
I think the most popular one that we have that is being commercially utilized is the powder bed fusion based additive manufacturing process.
Powder bed fusion.
Powder bed fusion. So as the name says, powder bed. So you'll have a metal powder, usually between 10 to 15 micron size. So again, you have a closed chamber, you have a powder bed, and then you have a mechanism to keep putting a very thin layer of powder on a
Bed.
bed. So the term that we use is substrate in additive manufacturing.
Supporting. Okay.
Yeah. So whatever material you are printing on, so that material is called as the substrate on which you would be printing. So here in the powder bed, you will have initially at the bottom, you'll have a substrate or a plate or a base on which you'll put a thin layer of powder. Then you'll have a laser which would scan through that powder on the powder, and then that will make that powder fuse to the substrate as well as wherever you scan the laser. So it would just, all of that would turn to liquid and just fuse together. And then this way you keep depositing a layer of powder, scan laser, deposit powder, then scan laser, and this way you can build a 3D structure. So it's very simple.
Interesting.
You just have a CAD geometry. You have to, so there is something called a slicing, where you convert the 3D geometry into n number of thin slices. Okay, and then those slices are fed to the machine that, okay, in this particular slice you need to move the laser.
XYZ. Okay.
Yeah, XYZ, you just need to move the laser this much. Yeah.
Wow.
That's how it happens.
Okay, that's one of the
That's one of the
advancement in metal 3D printing. Powder
bed fusion.
Okay, what are the other things
So
are there
other
in
one
metal?
which we just talked about, the extension of the welding, which is wire arc additive manufacturing.
Wire arc. So
Yeah.
how it is different from, okay, it is a solid only, there's no powder involved there.
Yes, there is no powder involved there. You just have a metal which you want to deposit. You melt it either using a laser or using by generating an arc like you do in the welding process. And then you trace the geometry.
Then, is there anything else?
Then there is a very sophisticated method which is electron beam melting based process.
Interesting.
So it's also a powder based. So powder based electron beam melting. So there also you will have a powder base, but instead of using laser to melt the powder, you would be using an electron beam. Now, for the electron beam to work in a particular environment, we need to have a certain environment, let's say vacuum.
Right.
So otherwise the electron, it will just, they will
Scatter
go haywire.
around.
Yeah. So that is, I think, the most sophisticated way of doing additive manufacturing. First of all, the electron beam, that head itself would be super expensive. Making a chamber,
Handling that,
handling all of these things, that's also
Why is
super
it
sophisticated. So in the electron beam process, the finish as well as the properties that you get are a bit superior to the
Laser.
powder bed fusion, the laser based process.
When precision and properties are precise, you use electron. Okay.
No, I think that would not be a right thing to say, because there will be audience who would be, who would be knowing a bit about these things. Think of the right terms to use there. You can search, right?
Yeah, of course.
It's an open book exam.
Was that correct? I think it was
Yeah, I was in the right direction.
overthinking.
Yeah. I mean, people came up with this electron beam based, very sophisticated method because it has some advantages. One is because you are doing the printing in the inert environment, so the oxidation is low and the scatter of the electron beams is low, and which leads to less oxidation, as well as the powder can be reused, whereas in the powder bed fusion the contamination of powder happens more with the laser beam, so the reusability is low. Plus the because it's an electron beam and the way, I mean, the setup is made, you can do very fast scans. So few meters per second is the could be the scanning
It's faster
speed.
than laser.
Yeah, so powder bed fusion usually you would go to about 1-2 meter per second. So with electron beam melting, you can go even higher than that. Plus the powder that you use in electron beam melting, that is bit coarse, some 50 to 100 micron. With powder bed fusion, it's much finer powder. But okay, I think that's not a
Very technical.
Yeah,
This is going right over
too
my
technical.
head. Right.
But I mean,
So these are the technologies
faster,
are coming
so the
up.
faster build rate and the
Less
most
impurities.
And the applications where this is mainly used are the materials which are prone to cracking. So one of the ways to prevent your builds from cracking during the printing itself is to preheat the substrate as well as the powder to a high temperature, maybe 800,000 degrees Celsius, and then do the printing. So for, let's say, titanium alloys, electron beam process is the go-to process. Then the next process is the directed energy deposition, where so it's one of the simplest process. So in powdered fusion as well as the electron beam based process, you need a powder bed. So that means you need large amount of powder to just start printing something. Okay, something in tens of kgs of powder. Now let's say you have very less powder and your powder is super expensive. Those are not very efficient processes that you would like to go to. So that's why we have this directed energy deposition. So what happens is there is a nozzle. So there are two coaxial nozzles. From the inner nozzle, the laser comes. From the outer nozzle, the powder comes. And the focus of the laser and the powder is the same. So you can control what could be the power of the laser and what would be the flow rate of the
amount
powder
of powder. Right.
Okay. And now, because the powder is coming coaxially, you can put your powder separately outside the machine. Okay, and you can work with very less powder, maybe as low as you can work with 100 grams, 50 grams of powder as also. And then as the laser comes, so the laser melts some part of the substrate, and then this powder comes. So while it is falling into that liquid, it has already reached to a high temperature. Sometimes it also melts and then goes into the liquid pool. And now because you are putting extra material, so you get a deposition. And then this way you just scan the geometry and you get a
Interesting.
part.
This is directed energy
Deposition.
Nice. I love this. This is a cool idea, right?
Yeah,
Laser and powder coming
it's
together.
so nice, so simple.
Okay. This is directed energy.
Yeah, this is directed energy deposition.
I'll write it down, otherwise I'll forget it later.
Yeah, so in terms of, I think the closer you would be to the geometry, so that would be the surface finish as well as the finest geometry or the section that you can build. So finest you can build are with powder bed fusion and electron beam. The smallest, thinnest geometries that you can build with DED would be slightly higher scale, and then the wire arc based would be slightly thicker geometry. So you can't, I mean, people are doing research to get all of this to very smaller scale so that you can get the resolution up to sub millimeter level, let's say 0.1 or something. So the thinnest geometry that we can print on our machine is about 1 mm. So that would be the resolution
better question
of the
would
print.
be, what 3D metal printing scientists are figuring out
Right now. Okay.
what is the intention? Like, in spite of having all of these techniques, electron beam, laser directed, powdered metal fusion, wire arc, directed energy deposition, everybody is working on different techniques. So what is the intention, or what are their focus?
I think a better question would be, okay, this technology has been there for now a couple of decades, and then there are so many research and modifications, improvements that have happened. But why don't we see this technology so much around us?
Right.
And why are we still,
Correct.
doing PhD and research on it?
Right.
So-
Why is it not yet mainstream?
Yeah, why is it not yet mainstream? Okay, why is it not used everywhere? Only in niche areas, like people use it for, let's say ISRO have used it to make some components.
Okay,
NASA
where and
would
all?
use it.
First, let's explore where and all it is being used.
Yeah, so mostly as of now, the additive manufacturing is used in non-load bearing applications. So by non-load bearing, I mean the components which are not under too much stress. So there are some components, for example, the fuel propulsion system, some complicated geometry, or a component which has, let's say, 10-15 different parts assembled together into one. So in this kind of, and those are done because you cannot directly make it through the traditional processes. So you have to make small parts and then assemble them together. So in such applications, we are using additive manufacturing. So that's one area where additive manufacturing is taking off. The other important area is biomedical implants. And I think that's the area that is that additive manufacturing has most touched. I know some people who have designed some implants, and their implants have been implanted in real people, and they are going on in their day-to-day life with it. So for shattered bones, where you cannot fix the bone, the fracture.
Right.
So there people will pull. Previously, people used to put steel plates, titanium plates, and those, getting a custom made, because everyone's physiology is different.
Every fracture
is different.
Right.
So now you want something which is compatible with our body. That's called biocompatible.
Right.
As well as which has properties close to our bone, so that later on, after a few years, it doesn't create any complications. So that's why the most common alloy that is used is Ti64. It's a titanium based alloy. So it's biocompatible. Its Young's modulus is close to our bone, and and now the researchers are making it as porous structure instead of a solid bone.
Nice.
So now inside those pores, your tissues can grow.
Blood can flow.
And it gets, it makes that implant a part of your body. So all of the tissues and the bone material would grow around the metal.
Nice.
So, and that's where the mostly powder bed fusion is used.
Okay.
Because inherently with the powder bed fusion method, you get porous structure. Okay. And that is not so good when you are going for, some machine component based application. If you want to put it into a machine, that might not be very desirable.
So that's where 3D printing is used in the,
yes,
has been an
majorly that
application.
is where it is
Biomedical
used.
one.
Biomedical
on the
implants.
implant side.
Yeah.
And one is on the
Aerospace
applications.
Yeah. So now we come to the point, why is it, not taken off? Why hasn't it taken off is because of its mechanical and microstructural properties.
What do you mean by mechanical?
Okay, you are printing a material. Okay, you got the geometry that you want, but then you also want the properties. Let's say you want to make a stand out of it. Okay. So if you're making a stand and then on the top of that you would be putting something. Okay. So you do not want that stand to buckle or to bend or to crack. So, and now that's a very simple case. Now in a machine, there will be so many vibrations and then other components sitting on it, or it would be subjected to all sorts of friction forces. Okay. So it should be able to withstand all of that. To do that, it should have certain mechanical properties. By mechanical properties, we mean that if you apply tension to it, it should sustain certain amount of tension, certain amount of compression. It should have certain hardness. So those are some of the mechanical properties. Then
Microscopic.
Microstructural properties as well. Now, to get a certain mechanical property, you need to go and look into what the microstructure is. And what the microstructure is dependent on how that particular material was manufactured. So that means, let's say if it came from a liquid form to, liquid solidified, how did it solidify?
Got it. There's a pattern everywhere.
So every small detail would lead to a change in microstructure and would lead to a change in mechanical properties. And we have not understood that well the microstructure or the solidification science during the additive manufacturing process, and that is what
research is pending. Big knowledge gap.
Yeah, that is where the gap is.
Microstructural properties of material manufacturing.
Yes. So how to get those particular properties, and can we get even superior mechanical properties?
Just playing with the microstructural arrangement of.
So I would like to give you an example. Okay, you would have seen in movies, that there'll be a swordsmith who would be heating the sword to a very high temperature, red hot, and then would hammer it, and then after he has sharpened it, then he would immediately put it in water, right? So that is what is called as quenching. Hammering is called as forging, and
putting into the water is
quenching. Okay. Now, why not leave that sword just as
on
it
its
is?
own?
On its own. Let it cool. That would change its properties. So if you do not cool it quickly, you will not get that strength that you want in this sword. So it would be little soft. So what it means is how you come from that melting temperature or from a very high temperature to its room temperature, and now there is so many things that happen there, and
movement
that
of
affects
atoms, arrangement, lattice,
yes,
microscopic gaps out there.
So how the atoms get arranged, what sort of phases form, microstructurally whatever happens at atomic scale and microstructural scale.
Okay, got it. So you mean we have not yet understood the microstructural things happening when additive manufacturing.
Yes.
So that would lead to different mechanical properties. So we don't get desired mechanical properties in 3D metal printing yet because there's a huge knowledge gap.
Knowledge gap is pending for lots of material. So the materials which are already have been applied at different places, we have some understanding of that. And the biggest challenge of additive manufacturing is whatever process, wire based, laser based, electron beam based, the directed energy deposition, the classic difference between additive manufacturing and the casting based processes is that in casting based process, you pour a liquid, you let it cool, or you put it in water or oil, you quench it. So it's a predictable cooling pattern. Okay, let's say you quench it. So all of the surfaces, heat would be extracted from all of the surfaces. So it's predictable, you can simulate, you can understand, And people have worked for decades and centuries to come up with certain kind of mold and the cooling mechanism for a particular material to get a particular mechanical property. Now in additive manufacturing process, because you are doing layer by layer deposition, so it's like you deposited some material in liquid form. Okay, so it turned into some small region, turned into liquid, solidified, but you are moving the laser or the electron beam. So locally, the parts are getting melted and then solidified.
Oh,
and
layer
then
by
layer by
layer.
layer.
Right,
So it's
right.
a very complicated heating and cooling cycle.
Added complexity.
Yeah, added complexity.
Got it.
So which is why, which is where the research is going on to understand the solidification process. And our lab precisely works on the understanding the solidification
Got it. The
mechanisms.
science behind it.
Yeah, science behind it.
Is there any other industry waiting for metal manufacturing, metal 3D printing to mature enough?
I think all sorts of custom printing. For example, you have a classic car which was manufactured in 60s, 70s, 80s. It's working super fine, but the company no longer does the servicing for it. There is
No
some
more spare
component.
parts.
Yeah, you don't have spare parts. So if you can get the geometry and what that material was, you can print it. So this technology might reach to common people and the need to have lot of spare parts because people would be giving annual maintenance contract and then they would be giving guarantee for a particular car or model. Be it any machine, any equipment that we have around, and there's a lot of inventory cost that is involved. So you can just get away with all of that if you have, let's say, 3D printers at several places across the country, and a customer comes, oh, we have this problem, and okay, fine, we'll get it in 2 days. They just manufacture it, ship it. Done. But we are not there yet.
That could be the future.
Yeah, but I think that is where it would be. It would penetrate so much into
That's on the consumer
community.
side.
Yeah.
Let's look at the industry. Aerospace is obvious part, making jet blades.
Okay, so wherever we have complicated geometries, as well as they need to be produced in low volume. So that's why right now the most applications that we see are in aerospace as well as in space, maybe the spacecraft and the defense technologies, aircraft, the fighter aircrafts.
And we have also seen 3D printed rockets. So that
Yes,
does that mean
rockets,
metal 3D printing, right?
Yes. So because if it's a low volume production, going through a traditional process, you would have to do several things like making mold, designing the process, and then going through all of that process. So it's a complicated as well as time consuming process. And then you want to make a small change in your geometry because you would of course have, because all of these are cutting edge fields.
Right.
And you would want to make some modifications into your design.
Iteration.
And now you have to, that small iteration, you have to again start the whole process. So that delays things. So, but in additive manufacturing, you can, because you have a 3D model of it, you just make that small change.
Nice.
Type, print it, test it out. So the lead time reduces. So wherever we have this kind of applications where you want low lead time, where there is lot of R&D required,
experimentations,
and low volume production, that's where as of now the
3D printing has been. Right. Right now we are in the cutting edge space technology, like rocket. 3D metal printing is used in making rocket nozzles and everything. So those are in the cutting edge. So what industries are waiting for this printing to mature? Like what are your predictions in 5 to 10 years?
I see most of the industries would want to. So I have seen people who are manufacturing some component using traditional manufacturing, and they are very curious about it. These days we see less metal parts around us. Most of them are made out of wood, plastic have taken over. But wherever you see that there is some metal component in it, I think all of that industry would want to use this technology because they can improvise the design very quickly. Wherever they have lots of assembling to do, that process can be simplified. When we talk about sustainability, we want to waste as less material as possible, right? And most of the subtractive processes, you remove so much material and it goes to waste, and then you again remelt it and then you reuse it. So in terms of, I think, the sustainability goals of the country as well as the industry, 3D printing would help them.
And how much, what do you think of the energy consumption of 3D printing and the regular manufacturing? Which one would consume more energy?
I think because additive manufacturing, we are incorporating lasers and the electron beams for a short amount of time. You have very high energy input, but then the whole process from its design inception till you get the final product, the overall energy consumption would be much lower
compared to manufacturing.
Yes.
Oh, okay. And manufacturing,
because see, you have furnaces which keep running 24/7. You cannot stop the production of steel. Okay, so it's a form of continuous casting process. Continuously we keep putting the alloy, all the raw materials, and then continuous production of steel slabs or whatever keeps going on. I think additive manufacturing won't replace the whole of the traditional technology, because there will be certain things which are to be manufactured in bulk, in large amounts, large volumes. So let's say the structural parts, the rods, the angles. So those, I think, would still be manufactured using traditional. That's more economical.
Right. Was there a particular event or industry or crisis that made people realize we need to start printing metal? Like, was there any urgency or something? Was it just research exploration to print metal?
So necessity is the mother of invention. So the overall prototyping process was a very long process. Now the implants that I talked about. Then we talked about the space and defense applications. So the lead times in all of this are very high, and the initial cost that you need to put in to make any of these components or the implants would be very high. So compared to that, the additive manufacturing reduced lead times as well as the overall cost of it.
So in your opinion, what's the biggest misconception people have about 3D printing? You have been working on this, so you must have your own colleagues from other fields talking about 3D printing, which you think they didn't understand or they didn't get it.
I think rather than having misconceptions, what people have is extreme curiosity. I don't think there are as much misconceptions, rather people have curiosity. I mean, whenever I tell, okay, I work on metal 3D printing. Oh, metal 3D printing. Oh, wow. But then metal melts at such high temperature. Oh, how do you do it? How do you make it? I mean, so people have lots of questions.
So, do you remember the first time you saw...
Oh, wait. Oh, there is a misconception.
Right.
Okay. Oh, good. Oh, but I can think of there is a misconception. Okay. A lot of people who do not understand the metallurgy part of things would think, okay, I'll just put in the geometry, I'll get material printed. For them, all that matters is if we can get the geometry right, all done. But there is so much that is happening to get the right properties. So that is where the people have misconception that, okay, I can. So unless you understand the physics, you cannot really, build something which is at par with the existing component level part manufacturing. Obviously, there are. I mean, I'm not denying that people are not doing that. I see that there is a lot to do there still.
Correct.
And that's what everyone who is working in additive manufacturing or the industry who would want to go into additive manufacturing, they really need to understand that it's not so straightforward. Maybe, let's say you will be able to take it here, but if you have a knowledge, you'll be able to take things much further.
Let's get into the materials, alloys, limitations, and breakthroughs. What kind of metals can we print today? And what's easy and what's difficult?
As of now, I think we can print almost any metal. There are challenges to print certain metals. We have the technology to print almost any material. If you can melt it, you can print it. Okay. But the problem lies in actually using a part or a component made out of those material and actually printing that material without defects. So let's say without cracking, with certain mechanical and microstructural properties, and that's where the challenges lie. And then there are certain materials, for example the titanium alloys, they are prone to oxidation at high temperature, and when you are doing 3D printing, so you are continuously heating and cooling. Okay. So whenever it goes to high temperature, there is a chance of oxidation, and oxidation is detrimental for the final properties of the material. So for that you need to prepare an inert environment
without oxygen.
Without oxygen. So you put it in vacuum and then you put in argon or any other inert gas into it, so that the whole surrounding of the print is in argon, so that oxidation doesn't happen. So as we talked about, there are some materials which are prone to cracking. Titanium is also prone to cracking.
So it depends on metal to metal. So if you understand the properties of a metal, then you can reverse engineer the 3D printer based on the
and
material.
Then there are certain materials which have very high reflectivity.
What do you mean by that?
So see, you are putting a laser onto the surface of the metal. Now, and it's just the light energy. So if it reflects most of the energy, you will not be able to melt it.
What are those materials?
So copper, aluminium. So now for this, there are certain different kind of lasers. So let's say green laser is used for that. Or if you want to melt copper, you can also use induction based heating or a wire arc type additive manufacturing process. So based on the material and the application, you would be choosing the particular process.
Okay. Again, then there would be variations in the manufacturing, right? Variation in printings.
Yes.
If it's this printing, this particular laser. If it's this printing, this particular laser of this frequency, other types.
But we would want to keep those variables less. Right. So mostly we stick to this infrared laser of the wavelength about 170 nanometer. Then there are some metals, let's say tungsten. It's a very high temperature metal. You will have to melt it at
2000 degrees.
2000, 3000 degrees. See, for example, the laser that we have, it's a 3 kilowatt laser. I think with this we can even melt tungsten. Okay, tungsten, molybdenum, all those high temperature metals. But then, as of now, we do not have an application to it. Once we have that, we can do it.
Why is not tungsten used in jet engines? Does nickel superalloy has a higher melting point than tungsten?
Nickel superalloy has better properties at those high temperatures. Now tungsten is also a heavy metal. You want to have the strength to weight ratio.
That also matters.
That also matters.
Right,
so that's why a lot of aircraft components are manufactured using titanium alloys. So it has higher strength for lower weight. And then also in automotives we see tungsten as well as the aluminium alloy components being used.
No, which is the mostly used metal for
steel.
printing? Steel.
I think steel and some of the nickel alloys, some Inconel alloys. So let's say Inconel 718.
Inconel means?
It's again a nickel based alloy which has nickel, chromium, cobalt, iron, few other things. Okay. Those are some classes.
Even that is a craft,
material.
no? Finding a right ratio and making an alloy is another craft.
Playing
with the variables. Amazing.
There are people in our department and across the world.
Wow.
Who are involved in alloy making.
It's amazing how humanity discovered alloys, playing with the different melting point and combining them, creating materials with the different properties, and we have come a long way.
Just 1% of a particular material would just totally change the properties of that material.
Right.
It's interesting, very fascinating.
So I looked at your research paper, the 2 papers you had sent me about your research. So I saw CMS X4
Yes.
shows up in a lot of your papers. What is it and why is it special?
So again, a nickel-based superalloy. So CMSX. Okay, what it means is, so the company which kind of invented this particular alloy is the Canon Muskegon.
Okay, got it.
Taking the name, I think.
So it came from the company name.
Yeah, correct. CMSX4. Okay, so I'll just dissect it. CM is Canon Muskegon. That's the company which invented it. SX is single crystal, is written in short form as SX. 4 is, they did lot of experiments over the years and decades, and that's one of the alloy. So it started with, let's say, CMSX, then they named 1, 2, 3, 4. So CMSX4 is the second generation of the single crystal nickel-based superalloy. In this second generation, what they added was 3% rhenium. So just adding the 3% rhenium make a whole lot of difference.
Okay, let's get into this then.
Yes.
Where it is used, why is it used, why that material is special?
This CMSX4 alloy, I mean, why was there a need to engineer this alloy? So when the aircrafts were built, and then when this gas turbine based engine, so it's not just the aircraft engines where it finds this application, but it's also in the power plants. But in power plants, you won't go to such high temperatures, but you still go to 800,000 degrees Celsius. These gas turbine engines are based on something called as Brayton cycle. Okay, I'll just simplify it. It's a thermodynamic cycle. If you want to extract as much energy as possible from this particular cycle, you need to increase the temperature difference between the highest point. Yes, the source and sink. So, which is the highest temperature? So, the highest temperature is at the exit of the combustion chamber. Okay, and the lowest temperature is the exhaust. So, you want to keep
the big difference between
biggest difference. But how low of the exiting gas could be, I mean, you can only get it as low as you can, maybe room temperature or something, or maybe a little colder. But still, even you cannot reach to the room temperature. I mean, as of now, we have advanced to get it to about 400, 500 degrees Celsius, the exhaust gas. Now, how can you increase the efficiency? You increase the temperature. But now, if you are increasing the temperature, you need the material
to sustain the withstand the temperature.
Withstand the temperature, and because it's a turbine, okay, so you have a big shaft on which there are these small turbine blades which are mounted, and they are rotating at thousands of RPM, and at such high RPM and such high temperatures above 1000 degrees Celsius, so they would be subjected to loading. So there is centrifugal force acting on each of the blades. And there are hot gases passing over it. The scientists realize that, okay, the failure of the blade that happens because of this phenomena, high temperature,
high
deformation, is what is called as creep. And so initially, I don't know, the engine manufacturers might have started with some material, but then eventually they came to nickel alloys. And then when they started making nickel alloys, they realized that, okay, if it has a polycrystalline microstructure, polycrystalline means that, let's say if you're looking at a microstructure, okay, you have lots of grain, maybe hundreds of grains. By grain, what I mean is, so metals, I mean, they are called metals because the atoms of metals or any alloy would arrange themselves in particular crystallographic orientation, and it's a repeated order. So a grain is comprises of all of the atoms which are nicely arranged in one given pattern. So they have one particular crystallographic orientation. Now there are lots of grains, and then all of them are of bit different crystallographic orientation. So now going back to the point that how we come from a liquid metal to the solid. So that would affect your crystallography,
So
the grain structure.
Got it.
Okay. Whether you will have whether you will have small grains, you'll have large grains. So they realized, okay, because there are a lot of grains, the creep failure happens sooner if you have a polycrystalline microstructure. So then they designed, okay, what if we
Single
reduce
grain.
that came later.
Okay.
Next, obviously, immediate thought they had was that, if we can just make it one single crystal, just one single grain, then that would reduce the creep failure and would increase the life. Now, you cannot directly jump from a polycrystalline to a single crystal. So you need to understand how you can get larger grains instead of having smaller grains. So you first reduce the number of grains. Okay. Then second part was they realized that, okay, most of the loading is happening radially. So if you have a blade, so it's only loading in the radial direction. So if, let's say, we do not have any grains which are perpendicular to it, that would also improve the life. So then the process evolved to making a columnar microstructure where you will have grains, but most of those grains would be single from bottom till the top. So that was one thing. Scientists were like, okay, how can we make it one single grain? So again, to make it a columnar grain, you cannot do it using a traditional casting process. You use something called as a bridgment type of solidification process where you have a temperature gradient. By temperature gradient, I mean, you need a liquid to be cooling. If you want a directional property, I was talking about columnar,
right?
So that is in one direction. So properties would be directional. So if you can control the solidification process such that the liquid solidifies in one direction, in that radial direction, if you can do that, then you can get the columnar growth. So that was the idea. So that led to development of
columnar.
Maybe columnar that might have been used for some other application, and then we can use this technology to make blades now. Then now they were like, okay, we want to
reduce the creep.
No, we want to reduce it to just one single grain. How do we do that? So one thing that happens is, the reason why we get the polycrystalline microstructure is because of something called as nucleation. So when something is solidifying, so a particular region, so if the temperature goes below certain temperature, so it helps in nucleating new grains or helps in solidification in that particular local region. So now because this nucleation happens, it is so difficult to start with a single crystal. You start a solidification process, there are going to be some grains. So that's where scientists, one thing is they tried to control this process as much as possible. They even devised it's a Russian name.
Okay, hard to pronounce. Okay.
Yeah, okay. So scientists, figured out a way so that, you can reduce the number of grains by starting your casting little bit away from your blade geometry. Okay. So you do something little bit away to reduce the number of grains. So you start the solidification little bit away from the blade. And then by the time the solidification comes here, the number of grains would be less. What if we have a material which has lower nucleation probability, and we use that? So they came up with this alloy which has a lower nucleation density, but also this has something on a microstructural scale which we won't go into, but I think I'll just mention it,
right,
that this has gamma prime precipitate microstructure which leads to much superior properties. Okay, we won't go into the details of that, but because of those, this particular alloy was invented, and then the blades they started manufacturing as single crystal.
Single crystal means grain is just
there is
one.
Just one single grain.
Wow. Okay. They
Okay.
maintain the uniformity.
So it was, I think, decades of work, several industries, working on their own. And then,
So what was the impact after that material
I mean,
invented?
now because you can increase, you got better properties, you have better creep life, so you can increase that
Temperature gradient.
Yes. So the temperature
Difference.
yes. The temperature at which the gases are exiting the combustion chamber. So you can now take those temperature higher, so increase the efficiency of the planes. So now you increase efficiency, your fuel consumption reduces.
Right.
Okay. The flight duration,
Cost.
the efficiency increase, so your power increased.
Nice.
Planes can go faster, they can go more efficiently, lower fuel consumption. You can travel longer distances with the same amount of fuel. Yeah, I mean,
Do you
so
know when
many
was this
advances.
invented?
Somewhere in 70s.
70s. Okay,
Yeah.
nice. Since then, they have been working on the same material to create a different generation of such
Yes.
materials.
So this was the second generation where they added rhenium as the element. Now it's a rare earth element.
Wow.
Okay.
Okay, tell me this modification of this alloy.
So this. So
No, first of all, how did they even think of adding rhenium? Like, it's such it's so
now,
crazy.
there will be people. See, in during the Industrial Revolution and all of the scientific discoveries were happening, people were inventing discovering new and new elements, and people were trying to do experiments and understand these particular elements. Someone would have mixed rhenium into something.
Wow.
First rhenium, they would have tried to understand rhenium, then put rhenium into something, then maybe it does this. Let's try putting a little bit of this, see what happens. That's how the material alloy design happens.
Okay.
So much of experimentation, so much of knowledge taken from the databases and whatever people have already done.
My God.
So it's decades and maybe centuries
So
of
many
work,
experiments,
variations and how it affects.
And what element and how much is the quantity of element to be added?
Yes.
It's like
And
crazy.
then again, how you solidify.
Oh my God.
Because that would change everything. If you solidify it faster, if you solidify it slower.
I mean, we
If
can
you-
still play with those variations and come up with much better much better products, right?
Yes,
Oh my
yes.
God, so
Okay.
much opportunity, so many possibilities out there. So what happened with the after rhenium? Somebody added rhenium, and
Yeah,
what was
somebody
the
added
difference?
rhenium. So that was one part. And also what happens in this CMSX alloy is that it has a strengthening mechanism which is based on gamma prime precipitates coming up in
What
the
are
gamma
those?
matrix. Okay, so I'll talk about that. So there are a lot of this small. So it's an alloy made up of about 10, 11 elements.
Okay, my God.
Nickel is about 50 to 55%. And then there are a lot of other elements. So now, how each of these elements combine with other elements. So all of these elements form a bond with nickel in the lattice structure. Okay. And if you go to a very fine microstructure level, maybe let's say few microns or under a microscope, if you zoom into a magnification of say 50,000, 100,000x, you will be able to see some small microstructure where, so you still don't see the atoms.
Lattice.
No,
How they are arranged.
What you can see is phase. Okay, a phase is chemically a similar region is one particular phase.
Too much competition is happening here.
No, there's so much going on there.
Right.
So as we are talking, you are understanding,
Yeah.
how much is the complexity of things.
Yeah.
Because of which, there is so much to do in additive manufacturing. So you can think of this gamma prime matrix like a brick and mortar wall. So you will build normal brick walls. In between brick walls, you will have the
Mortar.
Cement, mortar, which would bind all of those bricks together. So the gamma prime here is the brick and gamma is the mortar. What it does is, and both of them have different property, same as we have in a wall. Brick gives it strength, and the mortar around it, that makes it possible, that gives it structural integrity. That's what it happens here. So the gamma prime percentage here is about 70% out of the whole material. And if you check the microstructure anywhere, it would be about 70% of it. In all of the other nickel-based superalloys, you have much lower percentage of that. Now what this does is it gives you better strength and the mechanical properties. So along with lower nucleation probability, along with better strength properties, that's how we came to this particular material.
But just adding rhenium.
Yeah, and then adding rhenium, I mean rhenium again would have added this, improved the strength of it.
So that gave rise to fourth generation of this material.
No. So that is, it's called CMSX4, but it's actually the second generation.
Second generation of material.
And then after that, in the next generation, they increased the rhenium. They changed the composition of little bit other materials, but it is still not used as much. So something from third generation is CMSX10. So there are still less aircrafts flying with CMSX10, and because this was invented by a company. Okay. Now there are other engine manufacturers, Pratt and Whitney, and then Rolls-Royce, and then GE. They want to manufacture engine. Okay. So they, slightly modified the composition, and then they came up with their own composition, something very similar, but it would be slightly different, some different name. But composition wise about something similar. And then parallelly all of this development is happening. But the reason why we are still using CMSX4 in our research after almost 50 years of its
because a lot of literature is still anchored to that alloy, is it?
So it's like if you want to start something, if you start something which is well understood, well tested, there are lakhs of millions of hours of flight time that you have with this material. Okay. So getting a new material certified, again, that is a whole long process. And, who would be daring to, so it's like, see, okay, there is a material. Okay, if we use this material, it would give us maybe 5% improvement over the existing technology. One thing is economics, and other thing is risk. Who would want to, fly an aircraft, or would want to? One thing is, you would invest a lot of money into testing it rigorously, those aircraft engines mounted with the this newer material blades. But then people would always rather trust, it's just 5% increment. But we trust the other material more. Even the CMSX has its own problems. For example, lower machinability. It's prone to cracking during manufacturing. And then again, the next generation also have their own problems. Okay. And then to get a new material to the market, it takes time. So there is research going on where the scientists are trying to remove the rare earth elements out of it and make an alloy as good as these alloys.
Without rare earth elements.
Now there is a geopolitical and
China has a supply chain.
See, now rare earth element, India doesn't have rhenium. Some countries have it, China have it, US has it, Russia would have it, some European countries would have it. And because it's a material of defense importance now, because it is used in aircrafts, including commercial as well as the fighter aircrafts, and how good an aircraft is. So one of the parameter would be, apart from all the new technology sensors that we have, the engine is the heart of an aircraft. And to make a better engine, you need certain materials, alloys. Countries have, a much closer, a tight control over this kind of elements. So people would want to get rid of the rare earth elements. We get powders sometimes from Europe or from China. So it's so the time to get that material or the powder, that's a lot, but that's the geopolitical
position,
angle to it.
Right. So is it challenging to print nickel in a metal 3D printer compared to others?
I don't think so. If you know the ballpark, okay. You can do few trial and error. You know what power and at what speed and at what rate you should be depositing powder and what speed you should be moving the laser. Working with nickel, not
Right.
so difficult. There are
So-
some other elements which would be difficult to work with.
So if I gave you a periodic table
Okay.
and an unlimited budget,
Okay.
what's the dream metal you would love to print with and why?
Oh,
Have you ever thought about this?
I have not thought about it. But yeah, that's a very interesting question. It's a not a long-term dream. So you can't call it as a dream. You can call it objective that I would want to make single crystal prints out of this alloy. What's the dream metal that you want to print? It's more to do with application rather than
Then reverse engineer the
than-
metal.
yeah.
So what application would be exciting for you?
Oh, I would love to see a turbine blade manufactured using additive manufacturing in a fighter aircraft. Or and then eventually it would translate to a commercial aircraft. I would consider that as a dream because a design of a turbine blade and the material and all of this, the engine manufacturing, it's a decades of work and learning, and to be able to beat it and prove that this technology would prove superior to the existing technology. And because aircrafts go through such stringent compliances and testing, to see that in my career, that would
But
be
what
done
if
come through.
drones make fighter jets obsolete?
But then drones cannot carry the firepower
Right,
that
right,
the aircrafts would carry. But okay, I mean, even if you don't talk about the defense application, it's the commercial application.
Commercial, yeah. Same fighter blades can be used for the turbine, for the commercial, no? Power turbines.
Yeah. So it's used both in commercial
Same
as well
materials,
as
similar materials.
Yes.
Nickel-based alloys as
yes, all of them use nickel-based
well.
alloys.
Nice.
Even the turbine, the engines which are used for power generation, they also use nickel alloys, but they don't need as much the stringent microstructural requirements that we have.
Creeping standards.
Creeping and then the single crystal, they don't need that. So they use titanium and nickel alloys.
Now let's get into the physics.
Okay.
So now we shrinked ourselves and went inside that 3D printing, metal 3D printing, and we see things up close. So what are we seeing? What is happening when there is a metal is 3D printed?
So, I mean, as a part of my research, we don't go to the molecular level, but at molecular level, as we spoke earlier, that there is liquid where the atoms of the metal are, vibrating and moving at much higher speed, and the distance between them is larger. In additive manufacturing process, we start with a liquid metal and it solidifies. So those atoms then come together and then form a crystal lattice. And now how a particular lattice is oriented. So if there is just one single lattice which is repeated throughout the build, then we would call it as a single crystal build. If you have lots of grains in it, it will be polycrystalline build.
So one is solidification.
One is solidification that is happening.
How it solidifies.
Yeah, so that is what our group focuses on.
What decides solidification? What are the factors decide how that metal solidifies in that certain way?
There is something called as the length scale of the microstructure. That means when we are solidifying, I'll give an example of my system. Okay, so nickel superalloy. There will be a cooling rate at which it would just cool as a planar front. That means it's all nice liquid, and then when it solidifies, all of the elements are nicely homogeneously mixed and it is nicely cooling. Okay, but that process would be extremely slow. Realistically, we don't do it. So when we solidify, the rate at which we are solidifying, that would define how from the liquid the solid starts growing. So there are some structures called as dendrites. So you can imagine them as Christmas tree. How the Christmas tree is pointy, and then it has all of those arms. That's how the crystal grows. Now this crystal can have different anisotropy. That means you might have looked at ice crystal no, they form the
Right.
snowflakes.
Right.
That's also kind of a crystal structure. So the crystal structure would look something like that. When it's solidifying from this region to this region, I'm just magnifying some scale or a micron scale. It's solidifying from here to here.
Mm-hmm.
Let's say you're at the end of that mold or whatever process, okay, or at the substrate. If it's additive manufacturing process, okay, you have a continuous solid here. Because we are solidifying at a certain rate, and if that rate is above the threshold rate, this interface between solid here and then liquid here, so that interface will not move as a plane. So there will be some waves that would form
Between the solid and
the
solid.
interface. Okay. And then some of those waves would go, and then what you would see are something like fingers growing.
Dendrites.
Yes, and those are called as the dendrites. Okay, and those dendrites would be, and you have solid and then liquid pockets in between, and the solid, and then later even this part, this is complete solid, this is solid, this is liquid, and this is all space is liquid. So this whole thing
Continues to grow.
this continues to grow if you are maintaining the same solidification conditions. Otherwise it would change. So now what this leads to is that because different region have solidified at different time, and in an alloy you have several elements. Some elements want to stay in the liquid region, some elements want to stay in the solid region. So some elements would be more concentrated in the dendrite region, some in the interdendrite region. So the region which solidifies later. And in the microstructure, you will be able to see that signature as well. And it would have this kind of dendrite growth. If it's a normal columnar growth, you can see it right from the beginning till a large distance. If it's a polycrystalline growth, then in a liquid, you have something growing. But then if there are certain sites where the atoms can come and combine, so those are called as nucleation sites. So those could be any impurities that are there in the liquid, and that would act as nucleation site, and then there some solid will form, and then it would start growing outward in all the direction, and then based on what sort of symmetry it follows while growing. So you can have 6-fold symmetry, you can have 4-fold symmetry, and the structures look really beautiful. Let's say this was a small grain which nucleated and it grew. There was something which nucleated here and it grew. And when each of them are growing, they will be growing in the same crystallographic orientation. Whatever orientation it chose, the first guy who came there and whatever they started with, the first cluster, they would just continue growing in that direction. So let's say these are growing on the atomic scale. You have the crystal growing in this direction, and there is another crystal. So consider it as a cube, because we have in nickel superalloy, it's a cubic structure. So you have 2 cubes which are growing like this, and then they come and meet somewhere. Then they can't grow anymore, it's already solidified. And those form the grain boundaries. That's how the solidification happens and the grain boundaries form. And because you have inhomogeneity in the segregation of the elements, some went into liquid and solid, then also the rate at which you are cooling. So there are certain phases which would want to form at a particular temperature. So if you have stayed at that temperature, if it gets enough time, that phase could form there. So like this phase-based homogeneity comes, as well as this microstructural homogeneity. Then there is elemental segregation that happens. That's how even after solidification, so what I in my PhD majorly looked at is solidification and not the solid state transformation. That is, after it solidifies, what happens. Just to touch upon the solid state transformations, there are some processes which are used to make the properties as well as the composition more uniform in the part that you have manufactured, and that is called as heat treatment process. So once everything has cooled down, now you know, decades, centuries of research, and then that if this particular alloy, if you take it to this particular temperature, this phase forms. So then if it is desirable to have a certain phase and you want to remove some other phase, you would do heat treatment studies. So you would heat it to that temperature, let that phase form, let something precipitate. There's so many. I mean, it's again a whole different area of work. After manufacturing also there is something that is required. So be it a casting process or additive manufacturing process, what I said that the length scale is what would be different when you have a traditional casting process and additive manufacturing process. In casting process, it happens much more slowly. In additive manufacturing, you just solidification happens in fraction of seconds, where as in traditional casting methods, you would have it in minutes to hours. So that would change by the amount with which the elements are segregating. So accordingly, the post-processing that would be required would be different.
Do having dendrites and those things, the radial growth happening, is it a good thing in metal 3D printing, or is it part of
It's
not
a part of
processed,
the-
not done well? It's a part of the...
Yeah, I mean, it's a part of thing, you can't avoid it. You want to realistical time scales, you want to build stuff. Those will be there. So if solidification is happening, unless and until you are in an ideal situation, you will always get some kind of the
Dendrites
structures.
and-
Dendrites or could be some other structures also.
So those wouldn't affect the function of that material if it's used some elsewhere, like a jet engine.
No, so formation of dendrite doesn't directly affect the properties. What affects is because of the formation of dendrites, the composition variation that happened. So which would lead that locally the composition is different. Then essentially it's like a different alloy
Of its own,
composition
right.
sitting there, and it would have slightly different properties.
Weak point somewhere else.
Yeah, weak point somewhere. So that's why in all of these processes, we would go to something called as homogenization if we shrink ourselves and then go and watch how the process is happening. And that's also there's an approach that we took. Now, because that solidification is happening so fast within a fraction of a second, the laser we move is about 20 per second. And by the time it travels from 0 to 20 all the previously region, the initial
Deposited.
part would have already solidified. So it's happening in fraction of seconds. One thing that people do is you use high speed IR cameras to capture what is actually happening, how the liquid formed, and then how powder is falling, and then what sort of fluid flow, because powder is coming with some velocity and it's a liquid. Also, there are certain surface tension based flow, gravity based flow, lots of things happening there. Okay, if you want to understand solidification, since we do not have access to this kind of in situ analysis, so we took the approach of simulations. We created a model which simulates the heat transfer, the fluid flow happening, and the solidification that is happening as we deposit powder and scan the laser. And then we try to understand, okay, if we are, let's say, moving the laser at this speed with this power and with this particular powder flow rate, keeping all the other things constant, I mean, there are so many things happening there, then what effect does it have on the solidification? Okay, and what is really happening there in the melt pool? So that is something that we wanted to understand and visualize. And we wanted to create a one-to-one correlation between the simulation as well as the experiment. In simple terms, simulation is an approximation of a real process. Okay, you cannot be taking into account every small disturbance and then the acceleration of the CNC bed and then the environment, small impurities. So it's some ideal case. And from there we try to understand how the solidification happens, and then the thing that we try to extract out of our simulations are temperature gradients, the melt pool shapes. Melt pool shape is the liquid and solid interface. Okay, so that is something called as melt pool. So it would form a liquid pool, and then as you scan the laser, that liquid pool will just move, and the trailing edge of it would solidify, and this liquid pool would keep moving. Now that's very interesting to see.
Nice.
So we try to understand what kind of melt pool shapes are, and then what is the solidification velocity. You might be scanning at some velocity, but what is the velocity at which it is solidifying or the dendrites are growing. And then the temperature gradients at that interface. So these two factors, the solidification velocity and the temperature gradient, can tell a lot about the microstructure that you are going to get. In my research, as you have seen from my paper, we are working on single crystal alloy. So what we are aspiring to do is to 3D print something which will be of a single crystalline microstructure. Now, additive manufacturing in itself has all the conditions that are needed to get a polycrystalline or a columnar growth. Okay, getting a columnar growth, it inherently happens, but then getting a single crystal, that's the challenging part. So we try to establish a relation between what is the shape of the melt pool, what are your solidification velocities and temperature gradients to the microstructure. And then whatever machine parameters that you use, the laser power and the scanning speed, let's just keep these two as the variables. So laser power and scanning speed, and you trace it with this particular strategy. So now you can move laser in lots of different ways. You can just keep going in one direction and then come back to the starting point and then again start again. Or you can scan, go to the end of the part, come back again. Then you can do zigzag. Mm-hmm. So lots of things are possible. So we started with simple geometry. It's a single track wall. So a single track wall is you move the one track laser, you move up, you deposit next track on the top of it. So there is one track on which you will keep building. So it's a single brick wall that you will be building, so that we can control the process and understand
in a simple way. It's a simple structure to build.
Yeah, simple structure to build.
To build a single crystalline is the hardest one.
So that's the tough part. So through several trial and error, and then trying to understand, why is this happening in the experiment? We go back and then we run some simulations, and then from simulation we get the insight, I see. So this is what was happening in the simulation, and this is the reason why we observe certain thing in the microstructure or in terms of the build shape. So for example, if I fast forward our research, we did so many things, and then we landed up in this problem that we were able to print single crystal walls. We had two challenges initially to get to it. First was this CMSX4 alloy, it's prone to cracking. If there is high temperature gradient, that leads to high stresses being generated, which lead to solidification cracking. And you do not want your part to crack when it is getting manufactured.
Right.
Okay. So as we spoke about that, we heat the substrate to about 1100 degrees Celsius. We are not melting it, but we are heating. So, and the strategy we use to heat is you just use the laser itself, keep the powder off, and just move the laser on the substrate. That would heat up the substrate. Then once it has reached the temperature, then you go and start the deposition. So that takes care of the cracking issue. To get a single crystal wall, we had some single crystal substrate which we got through our collaborator, from which they had manufactured using traditional process. So they had a block. So we cut the small block and then we printed on the top of it. And so we had to engineer the right set of preheating, the laser power, the scan speed, all of that combined together, so that when we start printing, nothing nucleates anywhere during the print, as well as if we are starting with a single crystal substrate, we should be able to maintain that single crystalline growth. So, first cracking issue we were able to sort, and we were able to get nice single crystal growth in up to some height until certain region. And then sides were always coming, something was nucleating and some colors we were seeing. And we were wondering, we had lots of hypotheses. And then when we looked at the simulation closely, so we realized, so it's happening as a consequence of the way the solidification is happening. Okay, so because it's a single track wall, when the laser goes from this side to this side, you have deposited something, you go back, keep doing this. Okay, so what happens is, because the way the laser beam is and the way the powder comes, so because the parameters that we needed to get a single crystal growth, those parameters were at such a regime that at the edges of the wall, it was too hot, and then you will have some liquid flowing. So if you do the process slow enough, you can get the geometry correct. But because we were doing at the parameter range that we were doing, it was leading to non-conformity with the geometry itself, and which was changing the melt pool shapes, and that change in melt pool shape was leading to the bad parts that we were seeing on the edges.
So it's quite hard. So where do you think you guys are in the process of building single crystalline using metal 3D printing?
So as of now, we have been able to. So first of all, we wanted to understand the physics of things. Okay, so our lab has, previous PhD students and the current PhD students have done 1D solidification experiments. So they are called as directional solidification. You put insulation and you put high temperature zone, and then you put a low temperature zone. So you have a kind of a heat sink here and then heat source here. We are maintaining this temperature as well as this temperature through chiller, and the high temperature using some heater. And then you will take a crucible in which you will put the metal, either particle or rod, whatever it is, and then you would move it slowly, you would move it down. So when it is in the hot region, all of that would melt. Then when you slowly come to the solid region, then it starts solidifying. So that helps in understanding how the solidification is happening and how we can control it. So it's a simplified problem there. And because we were already working on, trying to grow a single crystal using that setup. So we were growing some small rods. So we thought, okay, why not can we build single crystal using additive manufacturing? That's how we got into this. Whatever understanding now we have developed. So you're asking what are the kind of parts that we have been able to make using 3D printing, the single crystal parts. So we were able to make and understand the physics of growing single crystal, single track walls, as well as 10 mm dia rods. So we have been able to build 10 mm dia rod of height 100 mm, one single grain.
Oh, okay.
So as of now, no other group in the world has been able to demonstrate this.
Congratulations.
Okay, thank you. Yeah, so that was kind of a
pride moment.
Yeah, pride moment. That okay, yeah, whatever we have tried to understand, and whatever papers we have written, and then there are a couple of more coming in, that would again talk more about the physics and how, if you would want to build any particular geometry or whatever you want to, if you want to print something, what are the things that you need to take into account, and what direction you should go towards.
How do you know it has printed in a single crystalline structure only? Do you subject it at a microscope, or do you take it for testing?
So that as of now, because we were in the testing phase, we would cut the sample, different sections, longitudinal transfers, and then polish, check it under optical microscope. If you see that all of those dendrite kind of structure, if you see same thing from the top to bottom, that means that's a single crystal. Then we verify that by going to scanning electron microscope and using the technique called as EBSD, electron backscatter diffraction, for different crystallographic orientation. So the electron beam falls on the sample, and then there is a detector which detects the backscattering of the electrons. So based on what is the crystallographic orientation at that particular location, it will tell you. So now you do it for the whole sample.
It should be the same, right?
So you scan over the whole sample, and then you stitch all the colored images.
Interesting. So if I were to request you to 3D print something, would like to 3D print my own YouTube channel named QHead. How would you go from start to the end?
Okay.
And also that should withstand like 500, 600 degrees temperature, like something shouldn't melt.
Okay. I mean, so we can take any high temperature metal.
It should be just like a jet blade.
Okay. So let's say we take stainless steel. Okay. First thing is I would want to know what is your geometry. So we would have to generate the CAD model of the logo that you have. Okay. How thick, size, etc., all of that taken into account. Then once we write that code, we put it through a slicing software, and then we convert it into a G code, M code. So those are the set of instructions that are given to the CNC as well as to laser, and then the powder feeder as well, to control what laser power we should be giving, in what direction, at what speed the CNC bed should be moving, and as well as what should be the powder flow rate. Okay.
For each layer, no? And
yes, for each layer. So you can design a simple thing where you can keep the power. So first we would start once we have this and once we have the code ready. So we have our own understanding of, okay, if we want to print this material, okay, this is the parameter range that we should start with. So we would start with what we already know, and then we'll do a trial and print it, and then based on whether do we need to vary the speed or the deposition rate or the laser power, so that we would do. So that's the experimental approach of it. Another way to do it would be to do a simulation. So I have a simulation model which can simulate this directed energy deposition process. So first we can go to the simulation. You start with some parameter, whatever knowledge you have, and then you see how the build shape is coming. Okay. Accordingly, you can tune in the parameters, do the simulation again. So, and then once you have optimized enough, you can come back here and then do the experiment.
Okay, now I want to ask, is always simulation and real print be the same, or will there be any difference?
So there is, yes. So for all the experimentalists, they would think, simulation is like how, okay, you just, there's some equation you are solving, something you are doing, and then you are just getting beautiful images, but how does it relate to the experiment? So for that reason, we need to calibrate for a particular material. We need to calibrate the simulation model. But then that's a one-time thing.
It's like fine-tuning the simulation with the data.
Yeah, because for material to material things would vary, and then as well as for geometry. So to a certain extent, you can rely, but let's say whatever geometry you would want to print, you should be doing the simulation with that geometry. So let's say I fix the laser power, scan speed, and powder flow rate. Okay. If I do just a single track wall, the layer thickness, that would give me a print. Let's say we fix that, okay, as our reference. And then if I go and want to print a blade or a rod, it might not be the same, because when we are printing a 3D structure, you will have some hatching strategy, some zigzag you would be moving. So you are depositing powder, okay, and next to it again you are depositing when you deposit the next track, and then again next track. So there is some overlap between those two tracks which you need to have, otherwise it will not fuse together, the two tracks which are going. So you would have some overlap. Now if you have some overlap, then the build height that you would get in just one layer, when you do 10 such scans and when you do just one scan, would be different. And also it would be different if you have a more complicated geometry.
Right.
The CMSX4 powder that we use, it costs about 1.5 lakh rupees per kg, somewhere from 1 to 1.5 lakhs.
Metal powder?
Yes.
Whoa.
So that's a very expensive powder.
The CNX, what is that?
CMSX4.
Okay, 1.5 lakh per kg.
Yeah, above 1 lakh per kg. I mean, we found some vendor who gave us around 1 lakh. Previously, we got it from 1.5 lakh.
My God, okay. So simulation is the wastage of materials.
Yeah, so you would
right.
You would want to limit your trials.
Like once you finish the solidification and it's in the form, so how do you test its usability? Like if you were to...
So there are a few things. One is you have to check the microstructure. So if you have optimized the parameters, there will always be a small variability which comes because of the laser and the environment. But more or less, if let's say you are printing 10 samples, they should be more or less in the having the similar properties if you have maintained similar conditions. So we would take one of them, we would do microstructure study, then we would take some small sample and do a mechanical testing of those samples. Then we would also do some heat treatment.
Mechanical,
study.
you mean at more stress? Huh?
No, I mean hardness is one part, but what is more important for us is the tensile strength. Then you put it through heat treatment because you have this composition variation little bit, as well as if you would want a particular phase to be there, so you want it to precipitate. For that you would put it through heat treatments, and then you would have the part. Again, I mean, based on what is the surface finish that you are looking for, you would have to do a little bit some machining of the component that you have manufactured.
So that's the whole process.
That's the whole process.
CAD to
everything.
testing.
Yeah.
So do you remember your first time seeing a metal 3D printer? When did you see it, and what went in your head when you saw it first?
So that was when I was in masters. I mean, actually it was not a metal 3D printer. I had seen a simple polymer 3D printer. I was like, yeah, nice. And then I used to see on YouTube, people making, small components, this and that using polymer 3D printers. And when I was in masters, so PhD student joined in our department. And so his background was mechanical and his bachelor's was in mechanical, master's was in mechatronics. So he had some knowledge of electronics and he had an interest in manufacturing. And he and professor, they decided to build a wire arc based additive manufacturing setup.
Where here, Indian Institute of Science?
No. So that was in BITS, Pilani, Rajasthan.
Okay.
And I was like, whoa, oh yeah. Oh, I was like, this is such a simple extension. I mean, you have a welding process. Now you just need to design a system around it so that you can move it to trace the geometry that you want. So he was involved in, designing all the, putting all the, even the PLC circuits together, then the fixtures, all of that he was designing. And then that is when I got very fascinated with this technology. That's one incident. The other thing was in my master's. So I did my master's in design engineering. And the idea was that I wanted to go into an area where I'm designing and building, making stuff. While I was in my master's, I was really inspired by professor from MIT, Neri Oxman. Okay.
Oh, okay. Big fan.
I see. Yeah, so
she combines biology and
architecture, biology, materials, computation. Yeah, okay. I got goosebumps just. And then learn a little bit of electronics, learn a bit of materials, mechanical, manufacturing, wood, metal, architecture, all sorts of civil and structural engineering, designing. Designs. So I was like, I have too many interests, and I was having a hard time to figure out what do I really want to do. And then it's not one place, where I can just fit in. So I thought research is an area because there is a possibility that you can work on several things. BITS Pilani was a very interesting place for me because there were bachelor students who were doing dual degree. Let's say there was someone who is in bachelor's in mechanical engineering and master's in biology, bachelor's in manufacturing, master's in biology or chemistry or physics or computer science. Then there are some computer science engineers with masters in economics. So it opened up so many areas. Like you can go into, so there's so much, it opens up so many different opportunities to be into. And so that was one fascinating thing. So when I was, trying to understand, where do I want to, what do? I have so much curiosity and I want to do this, that. And then I came across Neri Oxman, and then I was like, oh damn, okay, I just need to do what I'm doing at this point of time, and eventually I think things will fall into place. And then when I was just looking for, PhD opportunities abroad, I was like, okay, this is an interesting area. Maybe with my design background, okay, I can go into some biomimetics area. And while I was exploring, I saw this, that oh, she was, in a medical school for a couple of years. Then she was doing architecture. Then she went into
Material science.
Material science. And then eventually she was into fashion. And then eventually she has a lab where she combines all the things together. That made me think, okay, yes, so I just need to, keep doing what I'm doing. And then eventually I'll find, there will be a time where everything will converge. And then then later I came across this metal, the kind of wire arc based 3D printer that a PhD student was building there. And I thought, okay, yeah, this is also an interesting technology which can touch every walk of life eventually. And this also gives you that freedom that a designer wants. And then I just, with my supervisor, I got exposure to metallurgy and then some material science, simulation, computation, and application into some microstructural simulation. And then I realized, okay, there are very few people who are doing microstructural simulations, computational fluid dynamics simulations, which most of the mechanical engineers do. So a lot of people do that, a lot of industry do that. But the microstructural simulations and the understanding of the microstructure and the materials is that there is still a lot to do there, which would unlock a lot of opportunities. After my master's, I was just traveling around, visiting places, exploring where I would, because I understood that, okay, at this point of time, I don't see an industry there where I would directly fit in. I had that curiosity. I wanted to learn and get exposure to several things. So, and then when I visited IISc, I came across a professor here who is now my advisor, PhD advisor. And he had started working on additive manufacturing, and he was doing computational studies. And he told that there is a new 3D printer that is going to come. I said, yeah, I would be interested in, so-and-so stuff, building machines and then working on this technology. And he said, yeah, we are going to get that. And I was like, oh, that would be nice. Then later on, after working with him for some time, then I applied for PhD. And then because I felt that there are very few places across the world where you would find a lab which does theoretical study, computational study, the modeling, simulations, writing their own models, trying to understand the physics, going back to the theory, understanding things, as well as doing experiments themselves, and then finding a correlation or developing a correlation between simulations and the experimental understanding.
Process.
Yes, the whole thing. I felt this would be a very strong foundation on which later on I can, eventually I can explore stuff. And I thought, because it's, at IISc you have almost 40 departments and centers, and every department has so many things going on. So we'll get exposure to several things.
So that was your first experience.
Yeah, so that's how I
ended up in 3D printing.
Yeah.
So you've spent around 6 years in additive manufacturing.
Little more than 5 years.
Now I want to know what has been your most fulfilling moment in your research journey that you still think of.
Yeah. So first, after doing just some few experiments, then the machine that we had access to was down for a long time, and then parallelly I was working on simulations. We develop our own model to simulate this. We made some additions to some of the existing stuff which was there around, coded everything myself, and then did so many simulations. And then when we actually later on, when we did experiments, and then we used to, we got some info from the simulations, and then when we went to do experiments, we were like, oh, this is what we were seeing in the simulation. Oh, this makes so much sense. And then sometimes we would be puzzled about, why is something happening? And we would go back to simulations and then see, oh, okay, so we have to just keep doing the same thing. We have to look bit more, bit deeper into, and all those small details which you might think, okay, I mean, this might not be so relevant, and they make a difference. And then when we saw that, okay, when I was doing simulations, and then whatever geometrically as well as in terms of microstructure, whatever it was able to predict, and when we came to experiments and we did that, it was confirming to that. So that was such a good feeling.
To see the
So whatever we simulated,
accuracy between simulation and the real printing.
And the real printing, because that is the goal with which we started, that we want to develop a model and write a code such that if we do a simulation, we should be able to make a one-to-one correlation. Of course, I mean, we had to do some calibration,
right? But still, it's a complement to the calibration as well.
And the calibration process that we optimize to involves, I mean, it's not so difficult to do that as well. Okay, so that was a fulfilling moment. The next moment was when we actually, printed something, cut it, checked it under the microscope, and we were like, oh, this is looking all one single grain. And then also when we did the VSD, all of that looking one single color. And this was the last year moment. Okay. Then we were like, okay, yeah. So we have been able to achieve this much. We are happy about it, because even that much, whatever height we were able to get the single crystal, I mean, no one had demonstrated in this directed energy deposition based process. But then we were like, okay, we have come this far. And then that, but why is it, okay, why are we able to get single crystal up to this height? Why are we not able to go beyond that? Oh, why are we having this small bad region? So then we went into, further optimizing and thinking bit out of the box, like putting certain heating setup, cooling setup into the 3D printer, so that we can, control the heating and
solidification,
cooling, the solidification, and thereby the microstructure. And then,
so does that mean there is no other research happening in this field? So you guys are finding new knowledge by yourself?
Yes, something like that. A few years back, there's a group in Germany. So they were able to do single crystal builds using electron beam melting process. Okay, but they have mostly talked about the process, the characterization, the testing, and what properties they got, and compared that with the existing traditional things. Okay, but no one has talked about additive manufacturing and single crystal growth from so much solidification and physics point of view, that if you want to do it, I mean, how do we go about it? So I think our paper or our research work could be, one of that work which, if someone wants to work in this area, they would go and go up our paper.
Nice. That's a proudest moment, right?
Yeah. So that would help them speed up their work. They don't have to start from zero.
Nice.
They can take from our learnings and then start from wherever they would want to. Now, in the recent times, the proudest moment was when we got whole 100 rod as single crystal. Also, the wall that we were printing, 20 tall wall, that also we were able to get single crystal. And that is something that we would be writing in next few months.
Wow, this is all of 6 years of effort.
Yeah, that was 6 years. And then, because as a student before me, lot of days and nights of...
That's what was my next question. So instead of building all of that, how did your regular day look like here in the IISc?
Extremely packed, I would say, because there are so many new things that we did.
Packed in a sense, how many hours in a day?
I think on an average it would go 12 hours plus.
12 hours plus a day, okay.
Yeah, so let's say if I leave from my room at in the morning at 9:30, 10, I would go back to room 10, 11, 12, and it depends. Sometimes maybe a little early. So only breaks that we would take would be lunch. So breakfast, lunch, snacks. Yeah, and then in between, if we get some small pockets of breaks. Yeah. So this is not just my work. So I have one more colleague, Divya. So she was majorly doing the experimental work and the characterization part. I was majorly doing the simulation part of it. And so it was like we have there are two circles. We have certain independent work, and then there are some things where we both would come together. For example, when we have to think and brainstorm, okay, what we should be printing. And then when we are actually printing, observing how the print is going, and then noticing all those small things which might be affecting the properties and the microstructure. And then my advisor, Professor Abhik Chaudhary. So he was constantly there, always available. Most of the times coming, observing the experiments with us, being a part of the discussion, guiding us, helping us figure out things. Especially, so when we were doing modeling, helping with if I'm stuck, okay, this is the problem with the existing model. So, I mean, we wrote a new model. So that was because whatever existing models we had coded, we understood, okay, there are this problem. Okay, let's just make it simple. So inputs there, then when we characterize and then look at the sample, then having all of the discussion, okay, what might be going wrong? What are we missing? Yeah, so it's lot of work. Us three people
day and night.
Yeah, put together. And then along with that, of course, a lot of these funding agencies who made this possible. Then the operator of the machine, because we were using the machine from CPDM. The operator, they were there, Shiva. Then the management, then our department facilities. We use several common facilities. I think above all, our families. I think if they wouldn't have been so patient all this time, that we are so busy, packed on an average, we're clocking in so much time. I mean, it's extremely exhausting mentally, physically, both. And our families, sticking together through all of the tough times. Yeah. And then sometimes they would call and then I won't be able to pick the call, and managing everything at home, their own. I mean, so much of sacrifice of so many people, and then a lot of our work put together. Yeah.
Right. So how far are we from printing full functional aerospace component from your research? So if you go on the same pace that you're building,
yeah.
So how far we are from our own Indian Institute of Science manufacturing?
So I think on a lab scale, maybe in a year or two, we should be able to, a basic blade geometry, we should be able to get single crystal. But before that, we would like to try something that is repair of the blades.
What do you mean by that?
So most of these blades, turbine blades, would have a life of just 500 hours or 1000 hours fly time. Okay. After that, you have to
replace
check,
the blade.
And mostly you have to replace the blade. There's nothing much you can do because it has now gone into...
How much it cost?
What I have heard. I have never directly spoken with the people who purchased this, but I am estimating, somewhere around 10 lakhs.
Per blade?
Yeah. And like this, there are about 200 plus blade, I think 200 to 300 blades
in one turbine.
Yeah.
So you are solving quite economically important.
It is also more about, making our country more self-reliant. So,
right.
Because that's the heart of the engine. If we can manufacture the turbine blades, we can make our own engines.
So you mean you guys are 2 years far away from making inbuilt lab scale jet blade single crystal?
Okay, I won't go that far. I would say that maybe in a couple of years, for a simple blade geometry without its cooling channels and the current complexity, I think we should be able to get the single crystal blade in a couple of years. Then, but before that, as I was saying, we would like to do repair of the blades because every 500 or 1000 hours you have to throw them away. So instead, if we can, remove the bad part. On the top of that, you just do this using 3D printing. You patch up whatever the part was damaged.
Just like implant.
Yeah. So if you can build a little bit on the top of it. So if you have a broken structure, you just renovate. So if we can add a few hundred more hours to it. But then again, that's a long process. So it's not just about printing and getting a single crystal. After that, you would have to do some heat treatment. A lot of mechanical testing would be required until this process is certified to be used for the repair.
Interesting.
So
very good idea.
To actually get to the aircraft, okay. There's
a
a
lot of time. lot of testing.
Yeah.
That's your own original idea?
That was my advisor's idea.
Oh, you guys are very serious to taking it forward then.
Yeah, because it's a niche area.
So where does India stand in the global landscape of metal 3D printing?
In certain sense, we are, I would say we are still behind in actually adopting this technology, because what we focus more on is the economics of things. When it has to come into the normal commercial market, and also because the huge investment that would be required, and industries would already have a well established assembly line and their workflow. But I think that a lot of people, lot of institutes are parallelly working on different aspects of additive manufacturing across India. So in terms of the knowledge that we have acquired and what we can do, I think that would be, a lot of people are doing it at a global scale.
Have you guys ever had a conversation with HAL on this?
Yes.
Using their spoiled jet blades.
Yeah, we are in discussion. At least my advisor is in discussion with them. That's the future goal.
Nice.
If that happens, I think as a country we would be at a very good place, very good position, and I think even we would be feeling that pride accomplishment. Okay, we were able to do something.
Okay, now the last chapter.
Yeah.
So I want it to be imaginative. So let's build something together. So this is imaginative. Let's say I'm the CEO and you're the chief scientist of metal 3D printing startup.
Okay.
What are we building?
One thing is, first we would approach the defense organizations, we would approach the space organizations. They would have problems and they would have certain things which they would be happy if we can give something better or equivalent to whatever they have, but at a faster rate. Something better if we are doing in terms of lead time, in terms of the prototyping, in terms of the designing, any of that. And then in industry as well, several industries. So this is a little bit of market research that would be required. You would have to spread the word that we are doing this.
We are in the market.
And we are in the market, and we would like to do this. So if you have an idea, or if you have a problem, if you want to get a particular component or something manufactured, or you are having trouble making something, either with traditional process or with additive manufacturing, you can come to us and then we can give you complete solution, end-to-end solution.
Of any shape, of any material,
any material, any geometry. So we can help you with research to fit it into your pipeline, to get it from the material till the final product. We'll give the complete research, the manufacturing, as well as the service, and any further improvement or research that would be required.
That's a nice idea.
All of it, everything.
Approaching defense and space organizations, even they would have the budget to fund something like this, and they would have the requirement on prototyping. And
I think we all have heard in the news that there's a company, Indian startup, who has made a rocket almost completely out of using additive manufacturing.
Wow, okay.
There's a lot of things happening, and there's a huge market to capture.
Who are the first 5 people we need to hire to make this real?
So I need first and foremost 2 people. One, someone who is very good with finance and who can help us with, so that we have to focus less on the financial aspects of things. And that's one. Next is lawyer. You need a good lawyer.
Okay.
If you are commercializing something,
Right.
and then what IPs to protect. All sorts of things when we are negotiating, when we are signing MOUs with the industries, what sort of deals we would be making, how we would be pitching, all of that. Then I would need maybe a couple of more PhD people, or at least, so who would be able to brainstorm with me on this process. I mean, as of now, if we are talking about just 5 people, apart from these 2 people.
No, these are my other requirements, CEO's requirement on lawyer and all. You just focus on science and tech.
Only the science. There would be one thing, if we would want to make everything end to end and incorporate everything, so for now, I'm just assuming right now, or I'm considering that, machine is something that we will not be manufacturing. We'll get the machine, we'll have a collaboration with them. So we would have one person from their end who we would, have our own problems that, this is something we want to do. Can you incorporate this into the machine? So that would be, at least that one person would be required.
Customizing.
Yeah, customizing, and then, configuring this to our
machine
needs.
For our needs, okay.
For our needs. So I can't be doing all this stuff. So I would need a proper metallurgy background PhD
who has a good understanding on metal, metal.
Yeah, who has a good
alloys.
understanding of several alloys, as well as if they have an understanding of some solidification process or additive manufacturing process, that would be great. I would need one person in computation and modeling side. So we have 3 people as of now.
Yes, 2 more.
We need 2 more. I would obviously need someone who would take care of the machine, all the basic stuff, the printing. While we are doing the engineering
process
stuff, who would be, taking care of how, this has to be started, this has to be done, and then taking care of the printing process altogether.
Management, everything.
All of this technical side of things. Okay. One last person. Someone who is very enthusiastic, and someone who is kind of a good-hearted, curious, enthusiastic person who would want to learn this. Could be from any background.
Learn this from clean slate and make you guys question.
I would want someone who has a fresh perspective, maybe coming from mechanical.
Yes.
Or could be from some other background.
That's a good idea. That would be a nice team.
Obviously, I would need people who would do, when we are printing something, we would have to do characterization.
That is the later part, but so these are the 5 people.
Yeah, but even those people would be important. Without someone who would do the characterization and testing, I think I would need a team for that. I think at least another 2-3 people.
10 people size team, right? Almost.
Yeah. So that is, I think, bare minimum needed to maybe get started. So we will not be focused on just one thing. Okay, we would have a lot of diversity in the work.
Right.
Plus, it would be interesting. 10 different things happening.
Right.
Oh wow. Okay. Oh, this can be done. Oh, this can be done. Oh, someone comes up with a new material and they want to manufacture something interesting and challenging. So I think anything that would make us, feel every day that we are looking forward to do something.
Nice. To make it a reality, to have 10 people size team, to have those machines to manufacture those parts. So what is the funding do we need to start with?
Okay. Bare minimum. Yeah, I would say bare minimum just to start with, I think.
Nice space, all the machines, people.
No, I'm just talking about one machine to start with.
No, not one machine, just the whole infrastructure.
Okay. That would be tens of crores.
10 crores, 30 crores.
let me just think. Okay, let's say we get few orders where we want to make parts. So we need one machine just for R&D.
Consider 2 machines.
Okay, let's say 2 machines for R&D, and we would need few more machines as and when we
Scale
keep
it up.
getting as we scale, we would need more machines. So let's say we start with one production machine and one research
R&D
machine,
machine.
R&D machine, and then the other is
Production.
the production. Bare minimum, even if we get this two, and we set up the team, the place, and all these small things.
Systems, computers, simulators.
So, I think it would go to 10 crores.
Including team.
Yes.
Okay.
So we would be able to sustain for some time. Then there will be a lot of head that would be.
Right. I think we need 20 crores to sustain it for 1 year.
No, with a small team, until we start getting it to the production level, where we have a constant order, like someone wants us to manufacture or do something monthly, they want
Production.
something. Okay, so once we have that, slowly we can. I think I would say 10 crores. That is something that is needed, but I believe we can start much lower.
Okay, there is always
we can always start as low as we can.
Right.
There's a lot of you can get loan, you can get lease, you can get there's a lot of ways.
Loan is risky for this. So investment is the only.
Investment, and then there's several ways of doing it. But
what's the one thing we should never compromise on while running this startup?
The quality.
Quality, right?
Yes.
Once
never.
quality is gone, then no trust.
The quality and the relations that we make with the customer. Because if we do these two things right, I think everything else will fall in place. If we have the right people, we have right connection with the people, and we have trust between them, then I think whatever ups and downs we might come, I think we would be able to go through it and then come up better, stronger. And same goes with the team as well. The team that you start with, no doubt, has to be some level of risk taking, some level of courage, someone who is
Too much
very
experimentation.
Someone who is very level-headed, someone who is completely thinking out of the box, someone who is hyperactive. We need all kinds of people, but then more than that, we need someone who feels connected to what we are doing, because that is what will make them, that is what will keep everyone going in all their times.
Would you like to take this part as a startup co-founder? A founder, or start your own startup in this thing?
I would love to. So as I'm finishing my PhD, thinking about it, trying to understand, all the logistics, all the, small, there's so many things that I would need to work out to actually set up something.
Thank you so much for your time. It was fun talking to you.
Thanks a lot.
Yes.
Thanks a lot for having me here. And then in general, I would be anxious and I can't talk for. I haven't spoken at a stretch like this for so long without losing my center.